please welcome Dimiter Alexandrov of Lakehead University.
Thank you very much, colleagues. Okay, we're going to begin. You know me. I know the major part of you. In fact, it will be the third presentation regarding successful experiments, but they continue. Now, let's begin. Generally speaking, initially, the experiments which actually began in this field at my lab was published partially here, but they pertain to experiments using deuterium nitrogen mixture, gas mixture, not flammable mixture. And of course, actually, the corresponding results are valuable, but the corresponding excess heat is not too big. And we cannot say that the published results here, in fact, provide enough information that the corresponding technology to be developed. Further, however, the experiments continued using this actually gas chamber here and inflation of deuterium, molecular deuterium gas, having high purity, 99.995. It is important in order to ignore a possible existence of deuterium hydrate, which is important in terms of registration of helium further. So now, we have here a plasma source, but no plasma will be used. Simply, it will be used some kind of source of gas going in the chamber. The specimen here, consisting of constantan wire coiled on aluminum oxide rod, is installed here in this attachment to the main chamber. The purpose of this actually reactor is completely different. It's not connected with cold nuclear fusion reactions. However, the corresponding attachment must be done in order to proceed further. Now, by pyrometer and by optical spectrometer through the window, the temperature of the wire and the another temperature of the aluminum rod is subject of measurement. A residual gas analyzer provides mass spectroscopy analysis of the gases inside of the main chamber. And they're actually in situ measurements. Regarding the wire, constantan wire, it's actually scanning electronscope image. You can see precise diameter, 466 micrometers, okay? And the corresponding chemical content. It is actually EDX measurements. And here, the dominating chemical elements are presented. As you can see, nickel dominates here, after that copper, and not too much manganese and iron here. It is important actually because the conclusion that the major process will take place in the nickel clusters, but not only because nickel dominates, but because actually of the electron work functions between the nickel and the copper. So, this is actually the view of the attachment to the reactor, to the main body of the reactor. You see here the corresponding pyrometer, window here, and this is actually the view of the specimen through this window. You can see here. Now, the experiments, by the way, consider of, first of all, of confirmation that excess heat, the reason for the excess heat is injection of deuterium. We can see here experiment with nitrogen gas only. We can see for initial temperatures 300 Celsius and 400. Initially, what happens? Deuterium gas is subject to a step increase of the pressure. The temperature decreases because nitrogen gas having room temperature is cooling the specimen. After that, the temperature of the specimen was established to 400 degrees. I'm talking about the total temperature, not only the temperature of the wire. And again, we have step increase of nitrogen, of the pressure of nitrogen gas. After that, another step increase. And after that, another step decrease of the nitrogen gas. The temperature here increases simply because the nitrogen gas doesn't the cooling here decreases. The same experiment was repeated by deuterium gas. The same experiment. At 300 degrees Celsius, initial temperature, we don't have excess heat, and the incoming deuterium gas is cooling the specimen. That's why the temperature goes down. At 400 degrees, however, the same reaction is completely different. We can see here increase of the temperature. And after the temperature decreases because of the cooling of the specimen. Now, what is the reason about this one here? As a matter of fact, 300 degrees C corresponds to approximately 4 or 5 degrees C of the wire. And if the initial temperature is 400 C, the total specimen, it corresponds to 524 C of the wire. What is the reason? Something happens here. Something happens regarding energy release. And the muonic molecule model is applied in order this actually energy release to be explained. Why muonic molecule model? Because actually the first cold nuclear fusion reaction with energy release has been observed by Alvarez and his team in 1956, published in 1957. And theoretically, this actually process is very well described in this actually quantum mechanics in 1965. We have actually 2 deuterium nuclei here and 2 electrons, which are here. And here we have a crystal lattice of nickel clusters. All dark or actually black circles, they're actually nickels. These actually beige circles are nickels too. And these actually yellow circles are nickels. We have actually 2 electrons, which are given here. They belong to the conduction band. We have 2 deuterium nuclei propagating in the structure of the nickel clusters. Can they have propagate? They can. Simply because of the distribution of the electron charge in the crystal, in the primitive cell. Based on 3D 4s atomic orbitals, provides this kind of electron cloud. The potential energy, it is actually potential energy of the electron. It is above 0. That's why the incoming nuclei can propagate in the corresponding primitive cell. Generally speaking, we have decrease of the potentials in the points where we have nickel atoms and decrease of the potentials where we have 2 localized electrons. It is very important. Now, critical electron non-zone effective mass for 2 electrons. Just actually to clarify before I to continue further. Yesterday it was discussion regarding the electron effective mass. I'm going to tell the meaning of the electron effective mass here in this research. It means localization of electrons, of certain electron. Not because some matter is created in addition, but simply the electron is localized. This is important, as you're going to see further. So now, in order to get, if we have two electrons, in order to get energy release, we must have actually electron effective mass 153 M0. M0 is electron mass in rest. Now, it happens experimentally for a temperature 496, approximately 496 C, and theoretically it is about 510 C. Generally speaking, it is actually the formula giving expression of the electron effective mass if we consider the lattice vibrations. It is important to be mentioned, this fact, because actually this term here accounts for non-phonon couplings, for electron coupling, and electron couplings too. This term here. Now, in fact, something which is very interesting. We have actually two neighboring nickel atoms belonging to the crystal lattice vibrating with certain frequency for the temperature greater than the Debye temperature. Why Debye temperature? Because actually the phase is different for the temperatures above the Debye temperature. Now, we have here situation where actually both nuclei, here we have equilibrium positions, both nuclei move on opposite directions. Here, they move in order to join each other. Now, for the temperature about 500 degrees C, the shift of the nuclei of the nickel atoms in terms of the neutral of the equilibrium position is approximately 0.162 angstroms, and at this temperature we have overlap between two 4s orbitals, and at this temperature we observe energy release and excess of the temperature, which we saw on the previous graph. And it happens indeed for the temperature 153 M0, as the distance between both deuterons incorporated in the structure is about 6.4 times 10 to the power minus 3 angstroms, which is actually typical distance between deuterons in a muonic molecule. Now, let's go further. It is very important to be known that actually the distance between both electrons does not depend on deuterons. It depends on nickel atoms, because actually the masses of the deuterons are negligible in comparison to the masses of the nickel atoms. And the 4s orbitals, they belong to the nickel atoms. What happens? We have here logarithmic scale in both actually directions. Distance for S electrons. Again, this distance is subject of regular and is result of moving of nickel atoms. It is nothing to do with deuterium nuclei. Now, we have here a minimum. If actually we have distance here, simply hydrogen-like molecule will be created in the structure of indium clusters. However, if we short the distance, here we have electron couple attracting the nuclei. Now, the same is given in the scale, which is not logarithmic. Here we have hydrogen-like molecule minimum, it is below 0. Here we have maximum due to repulsion between two electrons, and here we have minimum, which actually creates 4s4x electron couple, attracting the electrons. Why it is important? Okay, because here talking, there is a screening of electrons. The question is, how does this screening occur? Okay, and there is a screening of the electrons. Where are they? How come the nuclei, two deuterium nuclei, must be brought enough close to each other in order they to join the electron cloud, and after that, nuclear fusion reaction to occur. Generally speaking, this actually d prime and d double prime distances have these things here. In the well, the localization of the electrons is connected with reduced value of the Compton wave. It's not necessary to have actually Compton wave belonging to, let's say, electrons having other treatment. We can treat exactly the same electrons in this way because they may be relativistic, they may not be relativistic. It is considered here that they're not relativistic. In this case, actually, the distance between them is this one here. But if the electron function, wave function of both electrons penetrates in this actually walls here, both deuterium nuclei will become on the distance 6.410 times -3 angstroms, like in muonic deuterium molecule, and the fusion reaction will occur. Now, before interaction here, you can see here the wire is heated by externally applied electrical current. Here, you see, during and immediately after interaction, there is no plasma here. We can see here significant brightness of the wire. We can see visibility of the rod. Here it is not visible, rod, and we have glow in the chamber. The corresponding temperatures here are given in this way. Visually, they're possible to be determined, despite of the fact that the determination in my experiments are done by, as I mentioned, optical spectrometer and optical parameter. I'm going to explain, if there is any question, how the temperatures were determined. Video, I'm going to provide this video later today. Now, what is the result? This is the initial temperature. If we have pulsing injection of deuterium gas, we can see here, after injection at time T1, the temperature of the specimen decreases. After that, however, despite of the fact that the deuterium gas is cooling the specimen, the temperature begins increase, which means that we have energy release in the wire. And at a certain point of the time, and this actually time T2, if we stop the deuterium gas, there will be no cooling, the temperature jumps up with about 100 degrees of the entire specimen. And this is actually a repeating process. Again, all actually part of the graphs which are above the red line means that they correspond to a temperature greater than the initial temperature achieved by heating current. 3 experiments I'm going to present here. Initial temperature of the wire is 671, 684, 694. The maximum temperature of the wire after interaction with deuterium gas, plasma is not used, is given here. It means we have approximately 400 degrees in these experiments. Approximately here is a little bit less. Here is approximately 400 degrees above the initial value. And this increase of the temperature happens for about 28 to 30 seconds after the ignition of the deuterium gas. Now, here we have the average release power in the experiments. Here we have the ratio between the output power and the input power heating the specimen. Here we can see 3.7 to 4.1. Here we have density of the released power per gram of the constantan wire. Significant density. The part of the chemical energy here is not more than 0.14% of the total released energy. There is a proof that it is not due to some kind of change of the electrical current or something like that. And this is the view of the specimen after many experiments. Almost new wire, almost new rod. How about here? Helium release. Okay, histogram is given here. Here we have actually, I'm going to point your attention to mass unit number 3, this one here, to mass number unit 4, and to mass unit number 5, which is actually helium for helium hydride. 3 corresponds to helium-3. Now, regarding helium-3 release, in order speculation to be avoided about correctness of the histograms, simply a ratio between helium-3, 3 atomic units, and 4 atomic units versus process number was provided. And initially, the corresponding energy released in the specimen was provided too. We can see here for the pulses, which are, and we can see strong correlation between the energy, these two lines, and between the ratio 3 atomic units, 4 atomic units here. There is strong correlation. The same is regarding actually ratio between helium hydride, 4 helium hydride, and 4 atomic units here versus pulse numbers here, and the corresponding energy released measured by the pyrometer. Reasonable questions. The released energy comes from cold nuclear fusion reaction in the constantan specimen caused by absorbed deuterium. Also, this conclusion is supported by relatively high density with released excess energy and by release of helium. No radiation. There is explanation. I can explain why there is no radiation. External radiation was detected. Now, before I to finish, I'm going to stop this one, and we are going to see the corresponding experiment, which is similar. Nothing happens now. Could you please help me? Maybe I have to stop this presentation.
Can I?
Yes. Stop the presentation. Okay. Okay, and now to start.
Now you can. Oh,
Okay, it's okay. I'm going to
I
stop.
think it's here already. Now you can launch.
Okay. So, just to comment this one here, we can see here through the window, here the pyrometer can be seen, it is in the dark room, constantan wire coiled around the aluminum rod.
Switch off light. Switch off light.
Thank you. Thank you very much. So now, the temperature of the coiled wire, of the constantan wire, is between 650 and 700 degrees C. Visually can be determined, despite of the fact that the pyrometer determines the temperature precisely, and the optical spectrometer. The rod is not visible, which means that its temperature is about 550 degrees C, and there is no glow in the chamber. It is before injection of the deuterium gas. Now, let's begin injection of deuterium gas. Okay, as you can see already, there is a glow. The brightness of the wire increases. There is no plasma in the experiment, and the rod is visible here, which means that there is release, increase of the energy due to increase of the temperature due to the energy release. Okay. Now there is some kind of equilibrium between energy release and cooling, because the incoming deuterium gas having room temperature is cooling the specimen. At a certain point of the time, we are going to stop the deuterium gas. I'm going to tell you exactly when is ready. Oh, it is visible already. You see what happens. Now, significant glow, the temperature is greater than 1000 degrees, the rod is very visible. There is no deuterium gas injection now. There is no cooling, but still reaction can continue due to initial absorption of deuterium in the wire. Now there is no further reaction. There is no deuterium. The glow decreases. The brightness of the wire decreases. The brightness of the rod decreases too. So it is typical cold nuclear fusion reaction, corresponding to one pulse of these things.
5 minutes.
Thank you very much for your attention. I finished. I appreciate your questions.
I didn't see the order, so okay.
Oh, okay, Italiano.
Okay.
So, 2 questions, very fast. Which one? Usually, commercial constantan has a composition of copper 55 and nickel 44. In your case, is almost nickel 80%. Do you have some explanation? First question. The second question, just speculation. According to my hypothesis, this is effect due to the flux of hydrogen in deuterium inside constantan wire. But it's just speculation.
Okay. Well, I don't know what kind of constantan I have used when I used to buy this constantan, but this is actually the real composition measured by EDX measurements, by scanning electron microscope. I don't know. It is actually typical.
Another company, each company is own constantan.
According to my actual information regarding this one, it has been created in Bulgaria, my native country, during the Cold War. Despite I bought online. I don't know why.
Me too. I have also 2 questions for you. First one, I ask you to know if you have evaluated the influence of the mean you use to heat the wire. Never you try to directly heat your wire by, for example, aluminum cartridge to evaluate the importance of the current crossing your wire. This is the first question. And next, I have been a little bit disappointed by your theory because you went on quantum physics side, you know. And for my, according to my understanding, I put some link between your work and former work from the French Carvan, you know. And in this way, for me, it's highly valuable to consider the gap in temperature between your surface and the ambient deuterium. I think it's highly relevant. And never you talk about that. Okay.
Okay. Could you repeat your question, but slowly, because actually I'm not sure that exactly. Or maybe if you can use some help with your colleagues in French. You know, actually they to translate English.
Which question? The first one or the second one?
The first question.
About your engineering, because you are heating your wire by direct alternative current.
Yes,
you know?
AC
But
current,
you never you have evaluated the importance of this means to heat the wire. Maybe the current generate a certain influence in your excess heat.
Okay, I'm going to explain here in this AC current is used. But if you use DC current, the effect is the same.
Okay.
There is no simply we have to achieve the same initial temperature. The effect is exactly the same. There is no any difference, which means we cannot expect some kind of influence of the AC frequency regarding this matter. What is your second question?
Yes, it's about the temperature difference between the deuterium and your surface. Because the deuterium you use, it's cold, it's ambient temperature, and it touches your constantan, which is heated. And there is a gap in temperature by 600 degrees. So it could be important to consider this point of view.
Okay, it is subject of additional measurements, but as a matter of fact, the interaction between it is connected with absorption of the deuterium in the constantan wire. Because actually, even after the removal of deuterium gas, still energy release increases. Later on, yes, later on it decreases because actually it is exhausted.
Okay. Thank you.
One is, did you use hydrogen instead of deuterium in time? And the second one is
Jean-Paul, I'm going to tell you. I expect why I'm not using, simply because of technical reasons. I cannot store two tanks at my lab simultaneously. No, it is typical one. Otherwise, I had actually intention to have a mixture between both gases and to proceed, but I'm not allowed to do this one.
Okay. The second question is, did you ever measure the resistivity of the wire before and after?
Generally speaking, before the experiments, after the experiments.
Yeah, how the material changed.
Generally speaking, there is no change.
Didn't change.
No change.
Okay. Thank you.
They are replicable experiments. There is not any change of the material.
All right, last question here.
Yeah, a few questions.
One
question.
It's okay.
Okay, with regards to theory, it seems like your theoretical explanation requires a pretty significant confinement of not one but two electrons. Have you calculated the localization energy of that confinement?
Localization of what?
Localization, there's an associated localization energy for the confinement of those electrons.
Very low. It is.
It's not very low.
No. I'm going to tell you. We are talking about localization energy between two electrons is very low. It is about minus. It is not on the top of my mind. Between -4 and -6 times 10 to the power -6 electron volts. Plus 6 mega electron volts. Significant, and it is due to magnetic interaction between both electrons, so that they approach each other, and they approach each other because actually the corresponding orbits approach each other.
Hold on, but if you're going to confine electrons, that's
Yes.
a significant energy charge. No, you're in debt. Probably hundreds of electron volts.
Yes, but it is connected.
Where does that energy come from?
Where this energy is coming from? Okay, this energy is coming from magnetic interactions between both electrons, only between them. Because actually, magnetic interaction at a certain point of the time, a certain distance, becomes much greater than the electric repulsion between them. And in this case, but we must achieve significant energy in order to shrink actually the electron wave function of this electric couple.
I'm not talking about the electric repulsion. I'm talking about, per the Heisenberg uncertainty principle, the energy required to confine electrons in a particular location. It's a very high charge.
Okay, no external energy because actually it comes due to overlap between both orbits. And the another actually matter comes here. Is it actually structure between two electrons stable? No, because actually when there is no overlap between both orbits, the structure will be destroyed. It means we are not talking about some kind of particle, quasi-particle, made by two electrons, having some kind of stable connection, and etc. Just actually, if we have overlap between orbitals, for s orbitals of the quantum, yes, we have. If not, everything is done. It's gone.
Okay, so I'm going to cut off here for local questions. We're going to break all the rules time-wise. We have an online question, so we're going to entertain that, and that will be the absolutely last question for the session.
Okay.
But here's the online question.
Dimiter, I have only one simple question. What means input power and out power in your table?
Okay.
How to measure output power? What's the methodic of the measurement of the output power?
Okay.
Tell me, please.
Okay, I'm going to tell. Input power means actually power coming from the AC current supply. Determined by
it's
electrical
current.
current, yes. Current and
Electrical.
voltage. Current and voltage. Now, the output.
It's simple.
Yes, the output power, however, and the real released output power is greater than the output power which is I presented, because actually I used only pyrometer and optical spectrometer using Planck's law for optical spectrometer and Stefan Boltzmann law for the pyrometer. In order, actually, this is actually the power which is radiated from the specimen.
It's very. I think it's not correct measurement of output power.
No, I agree.
Because of
It is much higher.
because
Not
of
much higher, but it
only
is
the
higher.
part, only one part of the total output power. It's
Is not actually total power is greater. Maybe not too much greater, I don't know. Because actually, in fact, only the power giving radiation measured by a pyrometer and by optical spectrometer is subject to determination. Other power, subject actually some kind of thermal conductivity or something like that, is not considered. Because actually, I didn't have opportunity to do this one. In this case, because the process is very, very fast, thermocouples don't work. Or at least actually thermocouples which are normally for slow process.
We're going to end the online questioning now. You can collaborate individually and contact each other to follow up.
Okay, fine. Okay.
Because we're running behind. But let's thank Dimiter for his presentation.
Okay, thank you very much. Colleagues, for your attention. Thanks.